Hello, I'm John Doherty, and this is another video in our series on nuts and bolts of using PEST and PEST++. This short video isn't really so short, but you can listen to it in parts if you'd like to. The subject of this video is implementing data space inversion. Before we talk about the nuts and bolts of implementing data space inversion, I'm going to say a few words about what data space inversion is and contrast this with the traditional way of extracting information from data using decision support modeling. So traditionally, if we're going to use a model to help us to provide support to decisions we have to make, we build a model. Now, if the issue that we're addressing is complex, if the hydrogeology, if the processes are complex, the model itself may be complex. So we build a complex model. We then equip that model with parameters. If the model is multi-layered, the model will require parameters in all of those layers. Ideally, parameterization complexity should be commensurate with structural complexity of the model. Perhaps we'll use pilot points in different layers of the model. Perhaps we'll use structural overlay parameters to represent structural features. We'll need parameters to imbue boundary conditions with hydraulic properties, possibly the historical stresses that we're not sure of. So now our model has lots of parameters. We ascribe a prior probability distribution to those parameters, based hopefully on the outcomes of site characterization. We then sample that prior probability distribution of parameters, so that we have many realizations of that prior probability distribution. Then, in what can be a fairly numerically intensive exercise, we adjust all those realizations until each one of them allows model outputs to replicate measured past system behavior. When all of these realizations allow the model to replicate what happened in the past, all these realizations are sampling the posterior parameter probability distribution. We then run the model into the future to sample the posterior predictive probability distribution. Now, this is how things are normally done, but it works often up to a point, but there can be problems. It's a numerically intensive procedure. It requires many model runs. The more data we have, generally, the more model runs it requires. And we may not fit our field measurements particularly well. Therefore, we may fail to extract some information from those measurements. It relies on the adjustability of parameters. And for parameters to be adjustable, they may need to be somewhat abstract, such as pilot points. Therefore, they don't really represent the way that hydraulic properties behave, the spatial variability of hydraulic properties beneath the surface. And it's sometimes difficult to ascribe a prior probability distribution to real hydraulic properties, let alone abstract hydraulic properties as represented by pilot points. As a result, the uncertainties which emerge from this process are often only indicative, especially if we don't get a good fit with the data, and especially if the relationships between model outputs and parameters is nonlinear, which often prevents us getting the fit that we'd like. And also, especially if there is uncertainty in the prior uncertainty of parameters, as there will be if parameters are abstract devices such as pilot points. So this method of extracting information from data works up to a point. Now, let's contrast this with data space inversion at a very high level before we get into the details of how data space inversion is actually done. Traditionally, the flow of information from data to a prediction passes through parameters, the parameters that are adjusted during model history matching. Parameters, by construction, have to be adjustable. That is, they can wiggle. When they wiggle, they can express uncertainty. When they have absorbed or assimilated information from data, they wiggle less and therefore express the fact that uncertainty has been constrained by information. These constraints are passed on to predictions that therefore have less uncertainty. All the while, information passes from data to parameters which may be somewhat abstract and which may have a prior probability distribution that we're not sure of, through parameters to predictions. With data space inversion, the intention is to make the path from the past to the future a little bit more direct, so information can flow from data to predictions. It's enabled by a model, so the complex model, still has an important role to play here, but information does not pass through parameters because this complex model may not actually have adjustable things called parameters. It may represent the fact that we don't know exactly what's under the subsurface. We still will have to generate many stochastic realizations of hydraulic properties. We will have to run this model a few hundred times, but probably only a few hundred times, using different realizations of things we don't know, which will be often hydraulic property and boundary condition distributions in the subsurface. But we don't need to adjust anything in the model, so it can represent hydraulic property variability in far more complex ways, possibly using modern-day geostatistics and categorical representations of subsurface variability. For example, a fault may be here or there or nowhere at all. So it can represent what happens under the subsurface and the fact that we don't know what happens under the subsurface in far more sophisticated ways as we take a few hundred runs of our complex model to express what we don't know about what's under the subsurface and what we do know about what's under the subsurface, because all these expressions of hydraulic property variability are still based on a prior probability distribution. We may not exactly know that prior probability distribution, therefore we can vary it when we equip the model with different sets of realizations of hydraulic properties. But these few hundred model runs, and it's only a few hundred model runs, are used to build a statistical relationship between the past and the future. And it's this statistical relationship that then is used to constrain predictions of the future based on information contained in measurements of the past. So once these few hundred model runs have been done, and we've established our statistical model that links the past to the future, we then note the actual values of field measurements that were made in the past. And we can use our statistical model as the device by which we constrain predictions of the future by measurements of the past. Our statistical model then gives us predictions of what will happen in the future, predictions that are hopefully at the center of the posterior predictive probability distributions of what will happen in the future, and associate with those predictions uncertainties. It is this statistical model that we're using as our data assimilation device, because at this stage we put the big model to one side, and working with this statistical model is very much easier than working with the big model. We don't have to adjust parameters in the big model. Our prediction constraining device is the statistical model. So that's, at a very high level, the concepts behind data space inversion. Now let us have a look a little more detail of how data space inversion is actually implemented. At the time of recording this video, the PEST suite offers two mechanisms for implementation of data space inversion, or DSI for short. Let's look at the first and then the second. Theory first. So, as we've just been talking about, the first stage of implementing data space inversion is undertaking a few hundred model runs based on stochastic representations of things that I don't know, normally hydraulic properties of the subsurface. So I sample the prior probability distribution of hydraulic properties and run the model once with each one of these samples. I run the model over the past and I run the model into the future. Now in this implementation of DSI we just look at one prediction at a time, so let's look at this prediction. Let's represent it by these little dots. So at this stage, having run the model a few hundred times based on realizations of prior probability distributions of hydraulic properties, I've effectively sampled the prior uncertainty of my prediction of interest. But I want to do more than that. What I want to sample is the posterior uncertainty of this prediction of interest. So I have to acknowledge the fact that I have observations of historical system behavior, represented here by the red dots. Now I calculate model-generated counterparts to these observations. I'm representing them by blue dots and putting them into a vector called O for outputs. This notation will be with us for the rest of the video. O for model-generated counterparts to field measurements, S for, well, in this scalar, S for the prediction, which in this case is a scalar because it's just one prediction. So now I put the big model aside. I've done a few hundred model runs. That's all I have to do. And I focus on building a relationship between the measured past and the managed future. I add noise to these model calculated observations in recognition of the fact that field measurements are accompanied by measurement noise. So the relationship that I build acknowledges the fact that noise accompanies field measurements. Optionally, I do a normal score transformation of each one of these outputs to make things a little bit more Gaussian, so that the probability distribution of these outputs, as obtained through doing those few hundred model runs, allows me to create this normal score transform, which makes them look on an individual basis Gaussian, and this can often improve the performance of data space inversion. Now I get down to work and I build the statistical relationship which I seek between the past and the future. This statistical relationship is embodied in a vector of the mean of each of these model outputs, the mean of the prediction, here's the vector here, and the covariance matrix that links the past to the future. This is just a standard covariance matrix. It's an empirical covariance matrix because I construct it using standard formulas from which we take samples of a random variable or random variables and build covariances between them. I build this covariance matrix just based on the outcomes of the few hundred model runs which I've just completed. Now I have my statistical relationship between the past and the future embodied in this mean vector and this covariance matrix. Now I bring my field data back into play because now I want to condition the prediction of the future based on this statistical relationship. I ask, what is the expected value of this prediction? What is the uncertainty associated with this prediction? Formulas that are available from linear algebra and basic statistics provide us with the ability to answer those questions. Here is the mean value, the expected value, the value of the posterior mean value of the prediction. Here is the variance, square of standard deviation, the uncertainty of that prediction. These formulas are used by a program named DSI-1 that's available through the PEST suite to provide the expected value of a prediction and its uncertainty based on the outcomes of a few hundred model runs calculated in the way that we've just discussed. That's the theory behind DSI-1. Now let us look at how to use DSI-1. We start off with what I call a partial pest control file. This can be an entire pest control file, but all we need is the observation data section of a pest control file. This contains the measured values of a series of observations. This is what we use to condition the predictions that we're interested in. Now, in this partial pest control file, DSI-1 requires that the weights that we ascribe to observations is the inverse of the standard deviation of measurement noise. This will actually be varied when we talk about DSI-2 later. But DSI-1 requires that these weights be the inverse of the standard deviation of measurement noise. DSI-1 uses these standard deviations to generate random realizations of measurement noise. Complementary to this partial pest control file, we need a CSV file. This CSV file contains realizations of model outputs corresponding to measurements generated using different realizations from the prior probability distribution of hydraulic properties. A file such as this is easily produced using PEST PPIES with the NOPT max variable set to 0 or using PEST PP SWP. The first row of this CSV file must contain the names of the observations, the same names that were recorded in the partial pest control file, and in the same order. The body of the CSV file contains model outputs, stochastic model outputs of these field observations, but calculated by the model on the basis of realizations of the prior probability distribution of hydraulic properties. Then we need a second CSV file. This CSV file pertains to predictions. Realization names down the left-hand column, just as for the previous CSV file. And for the same realizations, we now have values of predictions calculated using samples of the prior probability distribution of hydraulic properties. Predictions are named in the top row of the CSV file. Stochastic values of predictions are provided in the body of the file. One set for each realization. Same realizations as we use to calculate model-generated counterparts to field observations. To run DSI-1, we type its name at the screen prompt. The first thing that DSI-1 does is to ask us for a seed for its random number generator. We can accept the default. DSI-1 uses random number generation to generate realizations of measurement noise that it adds to model outputs, the model outputs that correspond to observations. DSI-1 then asks us for the name of the partial pest control file that it must read. It then reads the file. It asks us for the name of a transformation file. Most times just hit enter for none. We don't want one. We'll explain this a little bit later. Then DSI-1 asks for the name of the CSV file containing model-generated counterparts to field observations. We provide the name. We tell DSI-1 how many realizations we'd like it to read from that file, and it then reads the file. DSI-1 then asks us for the name of the CSV file that contains predictions. We provide the name of that file. We provide the name of a prediction whose uncertainty we want analyzed and whose value, whose posterior mean we want calculated. We provide the name of that prediction. DSI-1 reads the file. Do we want to transform this prediction? We'll talk about this shortly. As I just said, for now we say no. Most times we say no. DSI-1 then asks, should it do a normal score transform so it can work in Gaussian space? Normally we answer yes to this question. The performance of DSI is better normally if we do this. So we answer yes and move on. DSI 1 prompts for the name of the file in which it will record the outcomes of its calculations. We provide that name. And finally, it asks for the energy threshold for SVD truncation. Read about this in the PEST manual. Normally when we're dealing with big matrices, especially matrices which have things to do with statistics, singular value decomposition is acting behind the scenes. When we do SVD on a matrix, we normally truncate where singular values get low. That way, when we're inverting matrices, we don't inadvertently amplify numerical noise. Generally, the best answer to this question, as stated in the prompt, is between 0.9 and 0.9999. I normally provide an answer at the upper level of that range. The outcomes of DSI 1's calculations do not depend much at all on the value you select here. So this is far from critical, but we have the option if you want it. Normally select a high number. Then DSI 1 does its calculations and records the outcomes of its calculations on its output file, in this case named results.dat. Let's have a look at the DSI 1 output file. The first part of the output file simply echoes information that we provided to DSI 1. It also tells us how many singular values it actually uses to do its calculations, how many singular values were included prior to truncation. The second part of the file is the part that we're normally most interested in. Here we have the prediction, the values of the prediction, the prior mean and most importantly the posterior mean values of our prediction of interest. Accompanying this are the values that define the 68 and 95% confidence intervals of that prediction of interest. So we have the expected value of the prediction after data assimilation, assimilating information from measurements of past system behavior, and we have the uncertainty associated with that prediction, the posterior uncertainty of that prediction as given to us through the posterior confidence limits of the prediction. The last part of the DSI output file provides a rudimentary analysis of prior data conflict. Now, DSI, as we've already talked about, is quite fast and quite amazing in its ability to provide posterior means of predictions that we're interested in and the uncertainties associated with those predictions. But its behavior depends on there not being any prior data conflict. Prior data conflict happens if we run the model many times based on stochastic realizations of the prior probability distribution, and model outputs don't span our observations. This indicates that there's something wrong with the prior probability distribution that we've ascribed to hydraulic properties, or perhaps some structural defect of the model. This crude PDC index, which DSI 1 calculates, for every observation it should be between 0 and 1. If it's not, then prior data conflict is indicated. So the way that PDC index operates can just be gleaned from an inspection of this picture. The blue lines represent model outputs calculated using different realizations of the prior hydraulic property distribution. Ideally we'd have a few hundred of these. I've just represented a few. The red dots are field measurements corresponding to model outputs. A field measurement has a PDC index of greater than 1 if it's greater than any of the model calculated counterparts to that field measurement, calculated using realizations of prior hydraulic probability distribution. The PDC index is less than 0 if the measured value is less than any stochastic model output of the same quantity. The PDC index is between 0 and 1 if if the observation is spanned by stochastic model outputs. This is what we'd like. This suggests prior data conflict. And if we have too much prior data conflict, then we have to question the outcomes of data space inversion analysis. Here in the third part of the DSI1 output file, the number of transgressions, less than 0, greater than 1, is listed. Now we've seen DSI1 in action, let's look at a variant of what we've just seen before, which often will be a convenient way to undertake DSI1 analysis. Here is our partial pest control file again, but this time it includes predictions as well as observations. Predictions are recognized as having a weight of 0. That's how DSI1 knows that these are predictions and not observations. The value, the observed value associated with a prediction is irrelevant because it's not used to constrain uncertainty. So now that our predictions are included in the same partial pest control file as the observations, we only need one CSV file. This CSV file now contains model outputs, stochastic model outputs that correspond to both observations and predictions. The top row of this file contains the names of observations and predictions, same names as in the partial pest control file, in the same order. Stochastic values of model outputs, that is, model outputs calculating realizations of prior hydraulic property distributions, comprise part of the body of the CSV file, and stochastic model outputs corresponding to predictions comprise the rest of the CSV file. So now, and this file, by the way, is easily produced using PEST PPIES or PEST PPSWP. So now we run DSI1 again, and it's very similar to running it the same as we did last time. We start off by, in this case, accepting the default random number generator seed, provide the name of the partial pest control file, which DSI1 then reads. At this stage, we do not want a transformation file, so we just hit enter. Provide the name of a CSV file containing model-generated counterparts to field observations. We tell DSI1 that we want it to read 100 realizations of these stochastic model outputs. DSI1 then reads the file. It then asks for the name of the CSV file that holds stochastic predictions. We simply provide the name of the same CSV file and the name of the prediction that we're interested in. DSI1 then reads the file. The rest of DSI1's prompts are exactly the same as before. Do we want to transform the prediction? In this case, no. Work in Gaussian transform space? Yes. The name for the output file, we provide that name. We provide a energy threshold for SVD truncation, and DSI1 does its job. Before we leave DSI1, let's just have a look at this transformation file option. If we like, we can subject field observations and model generated counterparts to field observations to very primitive transformation. We do this if subjecting these outputs and measured counterparts to transformation provides a more linear or Gaussian relationship between the measured past and the future. And if we can establish this more linear or Gaussian relationship before we build our stochastic link between the past and the future, that stochastic link may be somewhat better. I very rarely do this in practice. This transformation, which is optimal, this simple transformation, is done before the normal scored transformation, which is nearly always recommended practice to implement. So if we do the transformation, it can be different for every observation. First, we can multiply that observation and the model generated counterpart to that observation by a scale, add an offset, optionally undertake log transformation of the outcomes of multiplication by scale and adding offset. And if the value is less than a certain number called base val, we move it up to that value before undertaking log transformation. So it's all very simple stuff and it's optional. If we judge that by subjecting stochastic model outputs and field data to these transformations, and optionally the prediction as well, which we'll see in a moment, improves the linearity or the Gaussianality of the relationship between what we've observed in the past and the prediction we're interested in. So we run DSI 1 again by typing its name at the screen prompt. The answer to the questions are all the same as before. Partial PEST control file, but in this case, when DSI1 asks us for the name of a transformation file, we actually provide a name. In this case, I'm calling it trans.dat. It asks whether it should skip a line at the top of this file. If there's a header in that file, we skip a line. So it reads the file, and internally it will implement the transformations, the simple transformations that we requested. DSI1 then prompts for the names of the CSV files, same as it did before, how many realizations to read, the name of the prediction we're interested in, and then it asks whether we'd also like to transform that prediction. If we say yes, it asks us for a scale, an offset, whether to log transform that prediction, and if we do decide to log transform that prediction, what the emergency base value is. That is, if a value calculated after application of scale, offset, and addition of a random number is less than a certain value, it's moved up to that value before log transformation. Do we work in Gaussian transform space? Normally, yes. What's the name of the output file? Results.dat again. Energy threshold for SVD truncation, 0.99 again, 999 again, and then it does its job. So that, very briefly, is how DSI1 works. We will now look at the second option for implementing data space inversion provided by the PEST suite. And this, I have to say, is the option that I generally use. It's the preferred option because it's more robust when statistical relationships between the past and the future are non-linear and non-Gaussian, which they normally are. So what we're going to talk about now, implemented in a program called DSI2, is normally the option we'd use to implement DSI, data space inversion, when using the PEST suite. First, the theory, very briefly. So just as before, we populate our big numerical model with many different realizations of prior probability distribution of hydraulic properties. We run the model, a numerical model, populated with these hydraulic property fields, these stochastic hydraulic property fields, over the past and into the future. In this case, we can focus on not just one but a number of predictions. These will be encapsulated in a vector S. Meanwhile, the model generated counterparts to our field data, encapsulated in a vector H, the model generated counterparts to our field data will be encapsulated in a vector O. At this stage, we've got our O vector, we've got our S vector. That is, we have stochastic model outputs corresponding to field measurements. We've got corresponding stochastic predictions. Optionally, we can undertake a normal score transformation of each one of these so that independently they have a Gaussian distribution. This often makes the DSI process, the outcomes of the DSI process a little better. Then, just as before, we establish a statistical relationship between the past and the future. This is embodied in the vector of means of O and S and an empirical covariance matrix that links the past, the measured past, to the predicted future. The elements of this covariance matrix, as before, are calculated using simple formulas derived from elementary statistics. Now we do things a little differently. Once we have our empirical covariance matrix, we subject that matrix to singular value decomposition. Having done that, we take the square root of the covariance matrix that links the past to the future. Having done that, we build a new model, a surrogate model, a statistical model, an extremely fast running model, runtime about 0.01 of a second. The parameters of this model I call PCA parameters because of how closely what we're doing resembles principal component analysis. The prior probability distribution of the parameters encapsulated in this X vector is simply the identity matrix. Each one of these elements of X have a mean of 0 and a standard deviation of 1 and are independent of each other. And it's easy to show that if I generate random realizations of X, the statistical relationship between O and S as generated by this model is exactly the same as the statistical relationship between model outputs and predictions as calculated by the complex numerical model. So this then becomes my replacement model. It provides statistical relationship between the past and the future. And when I undertake data assimilation through history matching, I history match this model, instead of the big numerical model, against field data. So I history match this model, and that allows me to compute predictions constrained by the necessity for model outputs to respect what happened in the past. I'm able now to calculate the posterior mean of any of the predictions of interest and associate uncertainties with those predictions. There are two ways in which we can history match this statistical surrogate model. The first option is simply to use PEST PPIES. This enables me to sample the posterior probability distribution of model predictions of interest. Option 2 is that I can calibrate this simple statistical surrogate model using PEST or PEST-HP, using regularized inversion, and then use a little utility named post-DSI mod to rapidly calculate predictive confidence limits, that is, posterior predictive confidence limits. The advantage of doing things this way is that the outcomes of the analysis are a little bit more stable, and we can avoid non-physical behavior of some predictions that sometimes accompanies use of a statistical model instead of a real model. Either way, the imposition of history matching constraints, assimilating information from field data, is extremely rapid because of how quickly this statistical surrogate model runs. The PEST suite provides 3 programs which allow us to implement this option of data space inversion. A program named DSI2 builds all the files we require for history matching. It builds the surrogate model and all the files that we require for history matching of that surrogate model. DSI mod is a general statistical surrogate model which encapsulates the square root of the covariance matrix that we just saw. POST DSI mod, as we just mentioned, is used for analysis for calculation of predictive uncertainty intervals. So that's the theory. This is a list of the software that implements the theory. Now let's use this software to see how it's done using the members of the PEST suite. We start off with two types of files that we've seen before: partial PEST control file and a corresponding CSV file which contains stochastic values of model outputs that correspond to field observations and model outputs that correspond to predictions. Program DSI2 reads both of those files. It then builds two PEST input data sets, two PEST control files, as we'll see. These files are very similar, but one of them is used for the running of PEST and the other is used for the running of PEST PPIES. These PEST control files are what we use to subject the DSI statistical model to history matching. So as I said, one of them is for the use of PEST PPIES that allows us to directly sample the posterior probability distributions of predictions of interest, or we can use PEST to calibrate the DSI statistical model. First we add regularization, then we calibrate that model using PEST or PEST HP, and this gives us predictions which are the posterior mean values of model predictions. A little post processor, which we'll see in a moment, called post DSI mod, then calculates posterior confidence limits of all those predictions. So we have two paths available to us. Let's look at the partial PEST control file. When using DSI2, this partial PEST control file must include both observations and predictions. It can be an entire PEST control file, but all that DSI2 reads is the observation data section of that file. Predictions are distinguished from observations by having weights of 0. This is how DSI2 knows that these are predictions. Now there's two options available here. In option 1, the observation weights should be the standard deviation or the inverse of the standard deviation of measurement noise. However, more flexibility than this is allowed. In option 2, we can actually provide the standard deviations of measurement noise. This allows us to use weights for computation of the objective function and standard deviations of measurement noise for calculation of the contribution that measurement noise makes to predictive uncertainty. Separation of these two roles is discussed in documentation for PEST and PEST++. Often it's good to use weights to balance the contribution to the overall objective function by different observation groups, ensuring visibility of those groups in the overall objective function. Standard deviation of measurement noise then is used to assess how much noise associated with measurements contributes to the uncertainties of predictions. So this is the option that I mostly use. We can associate measurement noise with predictions if we like. If we do that, post DSI mod can actually include so-called predictive noise when it calculates predictive uncertainty. Read more about that in the PEST manual. We won't be demonstrating that in this video. Note, by the way, that a pest control file can include comment lines just to make the contents of these columns a little clearer if we want. So complementary to the partial pest control file, we have a CSV file. This CSV file is easily built with PEST PPIES or PEST PP SWP or using your own software. The first row of this file must include the names of observations and predictions that were cited in the partial pest control file in the same order. The body of the file contains stochastic model outputs calculated using different realizations of samples of the prior probability distribution of hydraulic properties. The outputs corresponding to the past, outputs corresponding to the future for each realization. So the past, the future, on which basis we build the statistical relationship between the two. So now let's run DSI2. We run DSI2 by typing its name at the screen prompt. It begins execution by asking us for the name of the partial pest control file that it must read. It then reads the file. Optionally, we can do transformation of observations, primitive transformation of observations in the ways we discussed for DSI1. We don't normally do that, so I'll just press enter here to say I'm not interested in providing an observation transformation file. So DSI2 asks for the name of the CSV file that it must read, containing stochastic model outputs corresponding to field measurements, corresponding to predictions. It asks how many realizations of these outputs it has to read, and optionally it allows us to provide a CSV file in which observations and realizations are flipped in the CSV file. This can be useful sometimes. It then reads the CSV file. It asks us, do we want to do transformation to Gaussian space? Normally the data space inversion process works better if we do this, so we'll say yes. Then it asks a special question, which is only asked if we request transformation to Gaussian space. NST, or normal score transformation, is easy. Back transforming can be difficult if predictions calculated by the data space inversion process are near their extremes when assessed in terms of the range of stochastic model outputs corresponding to predictions. This normally only happens if we have prior data conflict, but if we do, we have to be able to handle it. Option 1 is normally the best. Read more about this in the PEST manual. Then it asks for the energy threshold for SVD truncation. As for DSI1, I normally provide a large number here, but the outcomes of DSI analysis are fairly insensitive, quite insensitive to the choice of this number as long as it's high. DSI2 is going to write a lot of files in a moment, so it asks for the file name base of these output files. We'll provide the name case_DSI. One of those files is going to be a pest control file used by PEST PPIES. PEST PPIES needs to know how many realizations to employ. We provide that answer in response to this prompt. DSI2 then writes all the files necessary for carrying out DSI analysis for our particular problem. Note that it's written two pest control files. This is done if we supply standard deviations of measurement noise as well as weights. If we don't, it writes just one PST file. And as I said before, normally it's a good idea to provide standard deviations of measurement noise as well as weights. So let's have a look at some of these files. The first file is the prior data conflict file. As we've already discussed, DSI works very well as long as we don't have prior data conflict. Its performance can be compromised if we do. So it's important to know our situation here. The PDC file, which DSI2 writes, contains a table. This table is very similar to the contents of the DSI1 output file, the same table that's written to the DSI1 output file. It contains a primitive PDC index which is ascribed to each observation. This tells us whether this observation lies within the range of stochastic model outputs pertaining to that observation. Ideally, the PDC index for each observation should be between 0 and 1. If it's less than 0 or greater than 1, then this is an indication either that our prior probability distribution for our hydraulic properties is not correct, or there's some structural defect with the model, or the model is omitting some important processes. Let's now have a look at the first of the PEST control files which DSI2 writes. This file is written for PEST rather than PEST PPIES. So here's the first part of the first PEST control file, the PEST control file that's written for PEST. PEST is told to run in estimation mode. We'll change this shortly. The parameter data section of the PEST control file lists PCA parameters. The initial values of these parameters are 0. Recall that their prior mean is 0. They have a standard deviation of 1. The bounds then are generous for these parameters. The observation data section of this PEST control file, the contents of this observation data section are directly transferred from the partial PEST control file which we supplied to DSI2. Here's the command that the PEST will use to run the surrogate statistical model. DSI mod, as we said before, is our general data space inversion statistical model. DSI mod takes arguments on its command line. The first of these arguments is the name of a binary file which makes the DSI statistical model specific to our case. This contains the square root of the covariance matrix that we discussed previously. This is a text input file which contains the current values of PCA parameters. This is an output file which contains model generated or DSI model generated counterparts to field observations and predictions. Case DSI2 told us that it wrote case DSI.bin, the binary file that the DSI mod statistical model requires. DSI2 also told us that it has written a template file for the DSI mod input file that contains PCA parameters and an instruction file to read DSI mod output. So everything is set up for us. These are details, by the way, that we don't really care about. I'm just explaining them to you now. When we're doing this in practice, we just simply use PEST to calibrate the statistical model. We don't have to worry about all these details. At the bottom of the PEST control file, the template and instruction files and the model input file, which is written on the basis of the template file, and the model output file, which is read by the instruction file, are recorded just as in a normal PEST control file. Okay, that's the first PEST control file. Now let's take a look at the second PEST control file that is written for us by DSI2. This is the PEST control file that is meant for the use of PEST PPIES. The first part of that file is identical to the first PEST control file that DSI2 wrote. It's the second part that makes this PEST control file specific to PEST PPIES. PEST IES control variables are recorded at the bottom of that file. Also, the observation data section of this PEST control file is recorded in an external file. This is a protocol that is permitted by members of the PEST++ suite. In this case, the observation data section of the PEST control file is recorded in a CSV file named case_DSI_obsdat.csv. Let's have a look at this file. It's a CSV file, more easily viewed in Excel. As you can see, this just reproduces the observation data section of the partial PEST control file that was supplied to DSI2. This includes weights and standard deviations of measurement noise. In the PEST IES control variables is the name of the prior parameter uncertainty file that PEST IES requires. It requires this file to generate realizations of the prior probability distribution. But because now we are dealing with the DSI statistical model, the parameters that this model uses are PCA parameters, and the prior probability distribution of those parameters must pertain to those PCA parameters. In that uncertainty file, the standard deviations of these PCA parameters are all listed. Because they're independent normal Gaussian variates, they all have a standard deviation of 1 as listed in the prior parameter uncertainty file. So, as I said before, these are all details. When you're using DSI2, you don't have to know all these details. You just simply implement the workflow, of which there are two options available to you. So DSI2 writes all the files necessary for implementation of two different workflows. Let's have a look at the IES trajectory first. Once DSI2 has done its job, we simply run PEST IES. After n iterations have elapsed, we can choose n. The information we want is provided in the .obs.csv file for that iteration as written by PEST IES. Here's an example of that file. The part of that file pertaining to model predictions is the one we're interested in. The DSI model has now been history matched, so the samples that are listed in the CSV file, the predictive outcomes are actually samples now of the posterior probability distribution of our predictions. We can take the contents of these columns and build predictive histograms in which we are now sampling the posterior probability distribution of predictions that we care about. Let's look at the alternative workflow trajectory. Recall that DSI2 has written us a PEST control file. We need to add regularization to this file. Therefore, by calibrating the model using regularized inversion, we will history match the model, and the predictions made by that model will be the posterior mean values of predictions of interest. To add regularization to a PEST control file, we can use the addreg2 utility supplied with PEST. To see what addreg2 does, just type its name at the screen prompt and it will tell you. In this case, we will ask addreg2 to take the PEST control file that was written for us by DSI2, add regularization to it, and in doing so write a new PEST control file called case_DSI_reg.pst. We will ask that the measurement objective function, the target measurement objective function, be 34, and we will ask addreg2 to set the regContinue regularization control variable to continue. Now it's your choice what that target measurement objective function is. That's something we won't talk about in this video, but there's plenty of discussion of what the value for the target measurement objective function should be in PEST documentation and in other videos. So we run adreg2 using that command line, and it writes a new PST file for us. If we have a quick look at this file, we'll see that PEST is told to run in regularization mode. PCA parameters are listed in the parameter data section, just as before. The PEST control file has a prior information section in which the preferred value of each PCA parameter is its initial value. The regularization section informs PEST the target measurement objective function, in this case is 34, and that if PEST is able to achieve that target measurement objective function, continue in its work until the regularization objective function is as low as it can be. Because the surrogate statistical model runs so quickly, continuing PEST execution in this manner costs us virtually nothing. So we just run PEST followed by the name of the PEST control file that adreg2 has just written for us. When PEST has finished calibrating the model, we can look at the model outputs corresponding to observations, but more importantly predictions, in the run record file or the residual file that PEST writes for us. So let's have a look at the bottom of the run record file. Here's the values of model outputs corresponding to observations. It will normally indicate fairly small residuals indicating good fit between surrogate model outputs and field data. The values of the predictions, which are not used to constrain parameters because they've got weights of 0, these values for the predictions are the posterior predictive means. This is what we want. These are predictions calculated by the surrogate statistical model, or would have been calculated by the complex numerical model had we actually calibrated it. But we don't. We use the statistical model to do the information harvesting. Now remember this slide. This is where we said to to make the statistical model specific to our case, this was the binary file which it required. We just need to know the name of this binary file because we're now about to run post DSI mod to obtain predictive uncertainties. So we run post DSI mod. If you want to know what it does, just type its name at the command line. We'll now run post DSI mod, supply the name of this binary file that makes the statistical model specific to our case, provide the name of the parameter value file which PEST produced with optimized values of PCA parameters, and tell it the name of a file to which it must write the outcomes of its deliberation. It does all that, and we'll inspect the file that it has just written. This file contains values of model outputs and their uncertainty, the limits of their uncertainty intervals. We don't care about model outputs that correspond to observations. What we do care about is model outputs that correspond to predictions. Here once again is the posterior mean values of predictions, and here are the confidence intervals of these predictions, calculated very quickly and very robustly using post DSI mod. If we do Gaussian transformation, we're working in Gaussian space, this file has an extra column. Remember I said that if predictions are near their extremes, then back transformation from Gaussian space to real space may be problematical. This is indicated if this rank value supplied is near 0 or near 1. This will normally only happen if we've got prior data conflict, but if it does happen, we really should know about it. So as long as all these values in particular, are not very close to 0 or very close to 1, then we don't have a problem in back transforming from Gaussian space to real space. If we do, it's normally an outcome of prior data conflict. We just need to be aware if this is happening. So to conclude this long video, let's just talk about the benefits and drawbacks of data space inversion. As I hope I've convinced you, data space inversion is easy to implement. Yes, there's a lot of detail goes on behind the scenes, and that's been explained in this video. But in implementing DSI, you only have to use a few simple commands. You have to run the complex model a few hundred times. The rest is easy, whether you're using DSI 1 or preferably DSI 2. Once we've done those few hundred runs of the complex model, the numerical burden is extremely light. That is, the numerical burden of extracting information from data, quantifying and reducing the uncertainty of predictions of interest. DSI is flexible. The prior probability distributions of model parameters can be extremely complex. In fact, the notion of parameters starts to change because nothing has to be adjusted in the complex model. We just have to represent the range of possibilities that may exist under the ground. That range can be described by a complex prior probability distribution that may include categorical variables that embody connected permeability, structures like faults or alluvial channels that may or may not exist, or may be here or may be there. All that can be embodied in the prior realizations used for running the complex model prior to building the DSI linkage between the past and the future. And we can accommodate uncertainties in prior uncertainties, all embodied in the realizations used when we run the complex model prior to building the statistical linkage between the past and the future. But whenever there's benefits, there's problems or drawbacks. DSI is fast and flexible, but if there's prior data conflict, then it's not going to work too well, because the integrity of the linkage between the past and the future is lost if the complex model, embodied with all those different statistical realizations of what may happen under the ground, if that complex model is still unable to reproduce what actually happened in the past. Then, of course, the relationship we build based on model outputs that are incapable of representing the historical behavior of the system, that statistical relationship will lose its integrity if the complex model doesn't have integrity. But that's something that besets decision support modeling, no matter how we try to harvest information from data. So that brings us to the end of this video. Thank you for your attention.